Hello. All right, let's get started. Number 121, best time to buy and sell stock. Easy. You're given an array prices where prices of I is the price of a given stock on the ith day. You want to maximize your profit by choosing a single day to buy one stock and choosing a different day in the future to sell that stock. Return the maximum profit you can achieve from this transaction. If you cannot achieve any profit, return 0. Okay. So let's think this through. We've got a bunch of numbers in our profit list. We get to buy once and sell once. We're going to want to buy. Oh, I should start my timer. We're going to want to buy on the day where the difference between the buy and the sell date is greatest. All right, so first obvious answer. Whoops. What's going on? I can't press enter on my keyboard. What's that about? My enter key is not working. That's gonna make things difficult. Shift enter is working, but enter is not working. Let me refresh this page. I have no idea what could be causing that. Okay, that's fixed. All right, so here's an obvious O of n squared answer. It's basically try every pair of days. The reason that's O of n squared is that you try every day as the first day, you try every day as the second day, and then you just see which one is the maximum. But I'm sure we can do better than that. I think we can probably do this in one pass. So what I'm thinking is like there's a recursive thing you could do also, which is for each day you either buy on that day or you don't buy on that day, and you return the max of those two choices. That's the naive recursion is going to be 2 to the n, because on each day you're making a separate choice and then you're branching. So let's not think about that too hard. I'm trying to think of a way to do this in a single pass. If I can't think of a way too fast, I'm gonna just do the n squared answer. All right, here's a few observations. You would never buy on a day where there was an earlier day that was cheaper. You would never sell on a day where there's a later day that's more expensive. You would never buy on a day where there's a earlier day that was cheaper. You would never sell on a day where there's a later day that's more expensive. You would never sell on a day where there's a later day that's more expensive. You would never sell on a day where there's a later day that's more expensive. Note 1, never buy on a day there's a cheaper day earlier. You'd never sell on a day where there's a bigger day later. Does that help us come up with something? Oh, I'm starting to think of some way you could do this. Basically, go through day by day, and as you go, keep track of what's the best you could be doing at this moment. So how would you know the best you could have done so far on this day? Or actually, maybe it's a little simpler than that. Because the other thing I'm thinking is, I can say something stronger about my notes. Note 3, you only buy in local minima. Note 4, you only sell in local maxima. So you're always going to be selling at a peak and buying at a trough. So we can kind of like anything that's going up or going down is dismissed. That's not going to be a place where we perform a transaction. So that reduces the number of candidates, but does it give us a way to figure it out as we go? So in this example, obviously, you buy at 1, you sell at 7. If I had a more complicated example that was like 10, or 1, 10, 5, 15, 10, 20. Then there's a tie for the best time to buy and sell between this pair, and this pair. Or no, actually, sorry. The answer would be buy at 1, sell at 20. All right, why is that? Because you always sell at the latest. Okay. Now I'm starting to think maybe there's a 2-pointer solution where the buy date we find it from the left side, the sell date we find it from the right side. Imagine I had like 120, a bunch of numbers bigger than my 20 here. It's not like you buy on the min and you sell on the max. Okay, so now thinking about 2 pointers. My buy pointer will start on the left side. Trying to think of how to apply these notes to a 2-pointer answer. You never buy on a day where there's a cheaper day earlier. So actually maybe my buy starts on the right side. No, because once the 2 pointers intersect, I have to stop. That's what I'm thinking at least, but I wouldn't. Be stopping otherwise. Or I wouldn't. I wouldn't necessarily have a valid answer otherwise. The answer is only valid if the buy comes before the sell. You'd never buy on a day where there's a cheaper day earlier. Thing is, that doesn't mean you can just start on the right and iterate left, because that would just give you the cheapest day. The point needs to be, it needs to be the cheapest day before the biggest sell. I'm not sure that the 2-pointer thing is the way. I think there's a way to just iterate from left to right, or possibly from right to left. So I guess at each point in the iteration, I can say the best that I could have bought it for so far is the minimum that came before me. And if I sell it here, I would make this much profit. So if I just go through all that and I remember the profit that I can make at each step, then I'll have the answer. So let's write that out. For price in prices, the things I have to remember are best so far, from math, important infinity. So my best is negative infinity, so I don't have to handle an edge case with none or something, or a 0 if the price, do the prices go negative? No, the prices don't go negative, so I could say best is 0. Actually, and it also said I have to return 0, so forget the infinity if there's no best answer. So there's best buy and there's best profit. On any given day, if price is less than best buy equals price. If price minus best buy is greater than best profit equals price minus best buy. Then at the end, return best profit. So why would this not work? This, I guess on this test case. Oh, I can't start best profit at 0. Or best buy at 0. I can't say the best buy price is 0. Let's bring back the infinity. From math, import infinity. Okay, this gives the right answer. And it's on time O1 space. Perfect. Yeah, so you're not going to do better than that. It's on space, or sorry, O1 space, because you're only remembering 2 extra variables. On time, because you have to look at each price once, so that is definitely optimal. All right, next problem. Restart the stopwatch. 122. Best time to buy and sell stock 2, medium. You're given an integer array prices, where prices of I is the price of a given stock on the ith day. On each day, you may decide to buy or sell the stock. You can only hold at most 1 share of the stock at any time. However, you can sell and buy the stock multiple times on the same day, ensuring you never hold more than 1 share of the stock. Find and return the maximum profit you can achieve. You can sell and buy the stock multiple times on the same day. Why would you ever want to do that? Wouldn't you be selling it and then buying it for the same price that you sold it? I think I'm missing something. Let's read the examples. Buy on day 2, sell on day 3, profit is 4. Buy on day 4, sell on day 5. Is there an example where you buy and sell on the same day? Buy on day 1, sell on day 5. Okay, I'm confused about this buy and sell the stock multiple times on the same day. I don't know why you would ever want to do that. Yeah, I just can't imagine that this ever makes sense to do. So, okay, so similar to last problem, but instead of 1 transaction total, it's as many transactions as you want. So the way we solved the last question is not going to apply. So how else can we do it? So we've still got the recursive thing. There's obviously the O 2 to the n naive recursive solution, which is on each day you either perform a transaction, so you buy or you sell depending on what you have, and then that just makes a big binary tree of size 2 to the n. Yeah, so I think we can do better than this is basically the try every single possibility solution. I think we can do better than that. So let's think about how can we do something like iterating from left to right and remembering the best thing we could, the most we could have made by now. So the difference here is I'm gonna draw a picture. Let me. So here I'm thinking the prices go up and down and up and down and up and down. Like before, we only care about the local minima and maxima. Those are the only times when we would ever want to do a transaction. Unlike before, the answer is not necessarily buy here and sell here, because we can sell at each peak. We can buy at each dip and sell at each peak, and that's going to give us the most profit. Because here the profit would be only the difference between this height and this height, but if you buy, sell, buy, sell, buy, sell, buy, sell, then it's like this is connected up here, this is connected up here, you're skipping all of the downwards and you're only buying the upwards. So that's going to be what we want to do. I think there's never a reason. Well, let's draw a different line and maybe we can give ourselves a reason. Is there ever a reason not to buy at every trough that has a peak that comes later? So I drew this with an overall upwards trend. What if it has an overall downwards trend? I would still want to buy and sell at each peak. Yeah. Okay, so I think it's like every time I'm holding and the price is about to go up, or sorry, the price is about to go down, I sell. Every time I am not holding and the price is about to go up, I buy. And then there's just the one edge case of just need to make sure that you don't end the at the end of the list you're not holding, because then if you are, you just like pretend you didn't buy in the last trough. Okay, so let's try that. Every time I'm holding and the price is about to go up, buy or sell, or if the price is about to go down, sell. And every time I'm not holding and the price is about to go up, buy. Okay. This should be ON time and O1 extra space. So holding equals false for price in prices. If holding and prices going down, sell. If not holding and prices gone up. Buy. Turn profit. So profit equals 0. We need to remember what is the amount that we last bought for. Buy, bought at. Okay, so another thing is I need to look into the future, so let's also have an index. Okay, take a look at the next one. All right, so if I'm holding and price is going down, what does price is going down mean? It means price is greater than prices of I plus 1. And then let's make sure that that's safe to do. Holding and I is less than len of prices minus 1, and price is greater than prices of I. Then we want to sell. So sell means holding equals false. Profit goes up by price minus bought at. Yeah, okay. And then if I'm not holding and price is going up, so that's, I'm allowed to look in the future, and the next price is, my current price is less than the next price, so the price is going up. Then buy, which means holding equals true, bought at equals price. Oh, okay. And if on the very last day I'm still holding, sell if that makes sense. Otherwise, pretend like you, on the last day, you're still holding. Sell if that would be helpful. Otherwise, pretend we never bought. So if holding. Profit. If holding and bought at is less than prices of the last price. Profit plus equals prices of the last price minus bought at. Okay, let's submit that. Zero milliseconds, 100%. Good, so we know this is optimal because, again, O1 extra space, we're just holding a few more variables. ON time, because we're just iterating over the list once. Next, 123, hard. Best time to buy and sell stock 3. You are given an array prices, where prices of I is the price of a given stock on the ith day. Find the maximum profit you can achieve. You may complete at most 2 transactions. Note, you may not engage in multiple transactions simultaneously, i.e. you must sell the stock before you buy again. You may complete at most 2 transactions. Isn't this the same as the first one, except we just... suggest that we... So the thing I'm wondering is this the same as the problem 121, except that instead of remembering the best so far, we remember the two best so far? I don't think so, actually, because you might want to, I guess the reason that might not be it is you might want to go back in time and undo the last two transactions. Best time to buy and sell stock 2 or 3. So one of the things I'm thinking is well, complete at most 2 transactions. Is this the same as the one? So let's picture. Here, let's pull up an image again. So we've got our market data. It goes down, it goes up. Let's have a lot of different edge cases here. How would we know what the 2 best transactions are? So one thing we know is that they're not going to overlap. It wouldn't make sense to, or actually, it may not even be allowed. Yeah, it's not even allowed. But it also wouldn't have helped to have the transactions overlapping with each other. So let me actually come up with some edge cases instead of looking at a random thing. So let's start with something easy. Let's say we've got this, this. So obviously the best 2 transactions are buy here, sell here, buy here, sell here. If you've got like jaggedness on the way up, and jaggedness on the way down, and jaggedness on the way up again, it's the same thing. Buy here, sell here, buy here, sell here. So let's try to make that example harder. The thing I'm just thinking is, we know how to iterate through and find the best place to buy and the best place to sell. The answer in this case is going to be something like buy here, sell here, buy here, sell here. It's going to be basically let me think about this. One thing I'm thinking is it basically find the best, find these two, the best buy and the best sell, and then and then find where you should split it. Once you've found that, and where you should split it is the place where it goes down the most within your best going up. Is it always the case that you can think of it as splitting up a going up? Well, if we had this, let's say the trend was going down. Or even just like this. Let's say it was like this. Then it's not a case of splitting it up. The best single transaction would be from, the best single transaction would be from here to here. And then you're not trying to find a split, you're just adding the second best to it. So sometimes the second best doesn't intersect with the best, and you just find the two best, and that's the answer. Sometimes the second best intersects with the best, in which case that doesn't help you at all. And then what you need to do is find the way to split the best into two. No, it could be more complicated than that, actually. It could be that it could be that they partially intersect, but that the second best is not completely contained within the best. Okay. So here's another silly way to do this. We know how to get the best in ON time. We know that the answer to this is going to be splitting the graph in two and getting the best from each side. So we could try every split and then find the best of each side. Try every split, find the best of each side. Trying every split, though, would turn this into ON. So well, sorry, would it do that? So that there's n ways to split it, and then for each split you have to do n. You have to do an ON traversal through it to find the best. So yeah, this would make it n squared. I just have the feeling you can do better than n squared. I think you should be able to go through the list once and find the best answer. Need to think about this for a sec. And we can do fewer than n splits. We can try a smaller number of splits. But in the limit, it's going to be n, because you could have a maximally jaggedy graph where it goes all the way to the max and all the way to the min on every other number. Then you would have to try every split. You never have to try a split while it's going up or while it's going down, because you know there's no transactions that take place outside of the local maxima and minima. Okay, I'm going back to thinking if there's a way to do this kind of like solution 1, but by remembering 2 things instead of remembering 1 thing. So it's something like you remember the best transaction number 1 you could have done, and you remember the best transaction number 2 you could have done. Does that make sense? So the best transaction 1 you could have done is going to be always the same as in the last answer. The best transaction 2 you could have done, the best transaction 1 you could have done is always just the best transaction you could do so far, doing only 1 transaction. The best place you could have bought minus the best place you could have sold so far. The best transaction number 2 depends on when you sold the first transaction. But I think that makes sense actually. So best transaction 1, best transaction 2, same as problem 121. This is start point after sale of transaction 1. The only thing I'm wondering is, would I ever want to go back in time and change? Yeah, because this is not the same transaction as this. It only becomes the same after you sell here. So this one is giving you new candidates for the one that's in here. Okay, I think maybe we're getting somewhere. So the thing I'm still struggling to figure out is, would I ever want to go back in time? Let's say I have a transaction 1 that I'm saving inside here, and I'm checking, is selling now or buying, I'm figuring out what's the best transaction 2 I can do from here. Then I find a new best first transaction. And I want to replace it here. I shouldn't have to go back in time because this transaction ends now, and these ones are always looking after the end of the last transaction, of the first transaction. Interesting. Okay, I think this might work. Okay, so we've got best. Best starts at 0. Best 2 starts at 0. Bought at 1 starts at infinity. From math or infinity. Bought at 2 starts at infinity. For price in prices. We've got to remember. Do we have to remember for holding? No, that was the. No, there's no such thing as holding here. Okay, so. The other thing we need is, when did the first transaction end? No, do we need that? We'll just start tracking it again. We might not need it. Let's see. Okay, so for price in prices, if price minus bought at 1 is greater than best 1, then this is our new best. Best 1 equals like the other way to say this is best 1 equals whatever is best between best 1 and bought at 1 minus, or price minus bought at 1. So this is, what if we sell now? This is the what if we sell now question. When do we buy? So when price is equal to the minimum bought at 1 is equal to the minimum of the current price bought at 1. So this is what if we sell, or what if we buy now, and this is what if we sell now. Okay. That tells us what the best price is going to be if we did one transaction. now we want to do 2 transactions. So so bought at 2 is equal to the minimum of bought at, you know what, I have to, I can't do this min stuff. I have to go back to having ifs, because if it's better, then I also want to clear out bought at 2. And say, like, never mind. This doesn't make sense. I just realized I do want to go back in time. Because I'm basically just, this answer is always find the best answer. No. I don't want to go back in time. I'm not going to replace stuff until replacing both works. The thing I need, though, is this is the thing, I'm just having trouble thinking it through. I need to remember what was the best first transaction so far. So best transaction 1. Best 1 and bought at 1 are basically candidates for the best first transaction. They're the best transaction. They're the best overall transaction from the beginning up to now. And then the second thing uses, this generates the candidates to be the best first transaction. So best transaction 1 equals I don't know why I'm having so much trouble with this. I'm going to go back to doing it procedurally, because that's going to help me deal with the second transaction at the same time. So if price minus bought at is better than best, best equals price minus bought at, so this is what if we buy, this is what if we sell. What if we sell also resets bought at 2 to infinity. No, it can't do that. That should only do that. Oh, come on. Why am I having so much trouble with this? Um, So I'm always finding new candidates for the best transaction 1 as I go. How do I know what the best transaction 2 is? It's not always the best transaction that happens after the overall best transaction so far. Because you might have to split the overall best transaction to get the answer. Although splitting the overall best transaction means it will be the best transaction. This is so hard to think about. So I've got all these days. I'm remembering that this is the best transaction so far. The other thing I want to remember is this is the best pair of transactions so far. So the thing I've been trying to say is that this is not possible. If this is the best transaction so far, then obviously the best pair of transactions would be this. If this is the second, it couldn't be that you take some subset of this, because this was the overall best. So it could be that it's this, and it could be that it's this, something like that, where you had to split inside the best transaction to get the two best transactions, or the best two transactions. So if we are at a certain number, we want to be remembering what's the best transaction so far and what's the two best transactions. What's the best two transactions so far? We know how to update this as we go. We're trying to figure out how do we update this as we go. We know that it's going to involve using this as your transaction number one, because the best two transactions so far, well, it doesn't necessarily include the best transaction so far, but at a certain time it will, like up to once we're here, when we were here, It will include what was once the best transaction so far. Yes. Transaction number 1 was once the best transaction so far. So we know how to generate the list of candidates, like as we go through the list once, we can generate the list of all the best transactions so far. That list could have O of n items, because if the transactions are increasing monotonically, then every transaction will have been the best transaction so far. If we try to fix that by only looking at peaks, it could still be the case, because then you could just zigzag upwards. And then there would be n over 2 times so far where you had the best transaction so far. Okay, so it's not just that you can generate the candidates and then iterate over the candidates and see which one's best. You know what? Oh, this is so simple. Another way to do it is 2 pointers. From the left, you're trying to find the best transaction so far. From the right, you're trying to find the best transaction so far. Once your 2 pointers meet, have you necessarily found the answer? Well, you could go all the way on both sides, but then you have to find the best between that where they don't overlap. And you might have n things to compare to do that, so you'd still be at n squared. How do you do this in ON? It just seems like you should be able to. I'm thinking about this 2-pointer approach again. I think this has legs. The thing is just you need to how do you know which side to expand? That I'm not sure. Because if you've got a lot of candidates on the left and a lot of candidates on the right, how do you know to that at the time that the 2 pointers cross, you definitely have the best solution? I'm not sure. Because maybe the best solution is going to be like, you've got a little bitty thing over here and you've got a huge transaction over here. And if you're going in from both directions, like the left side might consider this, and then this, and then this. Though actually it couldn't do that, because if it started considering this, it would consider the whole thing. Transaction 1 was once the best transaction so far. Okay, I'm starting to have an idea. Okay. If we pre-processed the array to generate a different array called largest after, where the value at each index is the largest value that comes after that index position. Then, as we're going through the days, we always know what the cell amount is going to be if we consider this day to be our buy day. And that applies to when we're looking for the best overall transaction, or when we're looking for transaction number 2. Because if you buy here, then you can sell anywhere until the end of the list. So since we know how to generate our candidates for this, the thing we want to do then, it doesn't let us skip right to the answer. The thing I'm thinking is, like, you've generated this, how do you figure this out instantly in O1 instead of having to go through the whole rest of the list? And you can find the end point instantly, but you can't find the start point. Instantly, unless no, you can't find the start point instantly. So this thing I've been saying about, like, you generate the transaction 1 candidates as you go, this is basically just the thing I said at the very beginning, where you find every way of splitting, and then you do the answer. You run the ON algorithm on each side. I'm just trying to think if there's a way to do it that's not equivalent to that. So we generate our candidates. let's say we did generate our left candidates and the right candidates. Maybe there's a way to match them faster. So here's all our left candidates. And then here's all our right candidates. And the thing is like match them and give me the biggest one that matches. So the way you could do that is you could sort the candidates by size, by like amount of profit, and that's going to give you left candidates ending later, and it's going to give you right candidates ending sooner. The reason being, or starting sooner. Here, like this. If you sort your left candidates and your right candidates by size, by amount of profit, you're going to get something in this pattern. The reason is it wouldn't be a candidate if it didn't end later than a previous candidate, because you're generating them as you go based on what's the best so far. So it only gets to be a candidate if it's better than one that came later, that came earlier. The problem is there could be a lot of matchings still, right? There could still, it's not like you can jump to the right matching from here. Like for so you can generate this whole thing in ON. That's 2 passes over the list. And then the matching is like, start with the first one. Binary search, you have the ending point. Binary search in the second list to find the earliest starting point that comes after that ending point. And that's candidate number 1. Or, wait, this is a little misleading also. So let's say they go all the way to the end. So the first one's not necessarily going to be the answer because it might not have a matching. Is the first one of these that has a matching the answer? No, because the first one that has a matching might match to a really low scoring. Wait, is it gonna? I feel like there's some properties that I might be missing. That makes the matching work better. Like this might not be a possible set of solutions because if this is a candidate, this can't be a candidate because you would have bought at the same buying point as here if this. No, that's not true, because you could have a big hole right here that's Actually, I think that might be right. The left side, the left side of any left candidate is always the smallest number we've seen so far. It's always the smallest number we've seen so far. So it cannot go backwards. So you could have this and this, but then you couldn't have this. It would have to come later like that. And then the right side, likewise, always has to come later also. Is that true? Yeah, because it wouldn't be a candidate if it wasn't better. And if it's better, that means it came later. So the left candidates look like this. What can I say about the right candidates? I guess I have to think about how do you even generate a right candidate. A right candidate is, I think the right side will always be the biggest number we've seen so far. So likewise, you can't go backwards. You have to go forwards. And the left side will always come later. Okay, so the property of both of these is that they always come later. The left and the right side are always greater or equal to the previous left and right side for the left candidates. And then for the right candidates, they're always less than or equal. Or the day that they're on is always earlier, is what I mean. Okay, this is getting very abstract. This is getting very hard to think about. So matching one of these two is what we want to do. We can generate these in ON. Our solution is a match between the two. They're sorted in order from, well, I guess these would be sorted from worst to best, actually. These are all sorted from worst to best. There could be O of n of both of them. This is going to be the hard part, is I can't just do something like iterate over the left answers until I find one that matches, because even if I do that, I might have to go over O of n. Somehow I have to jump to the right answer right away. Which makes me think this is not going to be the way to get to an answer, or to solve this problem. It's going to be something more like, you have to generate the answers as you go. I don't think this largest after idea can work either. Because if the thing is now I've generated this left answer and I want to know what's the best right answer. You know what? Actually, what I said earlier was wrong. I can iterate over n of them because I can generate them in on, and then if I find the matching in on, I'm still on overall. I didn't have to sort these. They came sorted from worst to best. Candidates from worst to best. I'm not sure how to generate these. That's still... Well, yeah, I think I know how to generate these. It's basically the opposite of how you generate these. Okay, so can I just go through this and find the best matching answer from the other side? So if I look at this, what I need to find is a solution in here that starts after this ends. So I think I could binary search on the start points, since I know the start points are in reverse order. That would give me an on log n overall runtime, because it's on candidates, and for each one I have to do a binary search, so log n, to find its match, and then I do that until I've found all of them. Until I found the best one. I do that over all of them to find the best one. What is this sort order? This, if this is just the order that they were generated in, then these are sorted from worst to best. Yeah, there's no way that I can just like start at the best. Because the best of the left side might need to be matched with the worst of the right side. So the fact that it's the best of either side doesn't tell me anything about where it's going to be overall. Okay. This is so complicated, but this is going to give me an on log n solution. On log n. Generate the left candidates and right candidates in on. Then match them. O log n with their best pair of it, with their best matching candidate, and return the most profitable. Um, okay. Let's try that. So we know how to generate the left candidates. Left candidates equals for price in prices. If price bought at equals infinity, best equals 0. If price minus bought at is greater than best, best equals price minus bought at, left candidates dot append. What do we need to know about a candidate? We need to know what its score, what its profit is, and where its right endpoint is. So let's enumerate over prices so that we have access to the index. Tuple int profit comma ending index. Okay, that's the left candidates. Now let's make the right candidates. So right candidates, we need to remember their profit and their start index. This is a little weird because we're iterating backwards. Can you even do that actually? Python list of reversed of enumerate range for. Enumerate object is not reversible. Can you cast it to a list first? Yeah. So we're doing something kind of weird when we're iterating from the right. The right side, we're not finding the bought at, we're finding the sold at. We're finding the right side of the transaction first. So, oh, also I forgot to update. Bought at equals min of bought at and price. Sold at equals max of sold at and price. And it starts at negative infinity. For, no, we've already got the for. So if price, if sold at minus price, so if we bought now and sold at that time later, that's still our profit. Best equals this. And right candidates dot append and I is now the left index. Yes. Okay, now we have our two lists of candidates. Now we're doing our matching. So for left in left candidates, left candidate in left candidates. Let me just do this without the binary search just to see if it gives the right answer to do binary search. So for right candidate in right candidates. If left candidate index, so at 1, is if it ends before the next one starts, less than right candidate index, then best equals 0. Best equals whatever is best between max and the total profit, which is left candidate at 0 plus right candidate at 0. So does that even give the right answer? Because we've written a lot of code. Not always. So when strictly increasing, oh, okay, I forgot. There's one extra candidate. No, sorry, that there isn't one extra candidate there. Oh. Okay. I guess I'm forcing there to be two transactions. If there's only one transaction, then I'm not finding the answer. So I'm trying to think of a way to cheat here. I think basically if I add prices equals prices plus negative, if I add a few negative infinities at the end, that gives space to do an extra zero profit transaction at the end. And this can't help you make profit, so I don't think it should change the answer. That didn't work. Oh, because I'm not gonna count it if it's infinity. Okay, let's just do you know, the other, or maybe a single transaction was best for candidate in left candidates. Best equals of candidate 0 best. Okay. Right now this is n squared, but if I binary search to get the right candidate, it won't be. So right candidate equals binary search right candidates. We have the right candidates, and what are we looking for? We're looking for a certain index. Index equals left candidate of 1. Let's define our binary search. Binary search. It's got candidates, which is a list of tuples of int, and it takes an index, which is an int, and it returns an index. Or maybe it returns the candidate. So you know what, I'm going to define this in here so I can do it. I can have the local variables in scope. I'm not going to define candidates. I know that I'm looking through the right candidates. I only am going to find the index. Find right candidate greater than index with start greater than index. All right, so binary search, you've got the left side, you've got the right side. It's equal 0 and len of right candidates minus 1. While the left is less than the right, you either shrink to search the left side or you shrink to search the right side. So midpoint equals left plus right over 2. If right candidates at mid, the index, no, the score, no, the index, if the index is less than index, so I picked here, we've got, this is our search space, this is our middle. I'm trying to find the first one whose I'm trying to find the first one whose index is greater than index. So if the thing I found is less than index, then the thing I'm looking for is on the right side. So L equals mid plus 1. Elif, the thing I found is on the right side, then if it is greater, the thing I found is greater. Let's say if it's less than or equal, then I know that my answer is on the right side, so I push the left forward. It's greater than my answer's on the left side. Yeah. And it might include mid. At the end, return right candidates of L. I always have so much trouble implementing binary search for some reason, so there's no way this will work on the first try. Well, first of all, I forgot to change the signature here. It's going to be off by 1 in many different ways. I just have trouble not doing that. L is out of range. Well, okay, it should be R because that's the one that might have the answer at the end. My parentheses are wrong here. You shouldn't just divide the right side. You should divide both of them. Did I actually get the binary search working properly? There's no way, but let's see. We got pretty far getting the right answer on most things. Wrong answer on this question, 613247. So the best you can do here is buy sell and then buy sell. So this one would give you 6 profit, this one would give you 2 profit. Or sorry, this gives you 5 profit, this gives you 2 profit. And why don't I find that? So let's, at the end here, print left candidates and right candidates. What did we end up with? So our left candidates are ending at 2. So it's saying buying this would give you a profit of 2. This would give you a profit of 3. And this would give you a profit of 6. So the left candidates are correct. The right candidates oh, you know what? I was assuming that my right candidates indexes are ordered, but they're the other order. They're in decreasing order. So if the midpoint that I found is less than or equal to the index I'm looking for, if the midpoint is less than or equal, midpoint's less than, and they're in reverse sorted order, so stuff that's greater than will be on the left side of this, which means R needs to shrink. And then the other way. And then the thing I'm trying to figure out is, do you do -1 here? If my, yeah. And then L, I should do L here, because that's the one that could have the answer. Oh, and obviously I've got some kind of infinite loop because of my off by one stuff. Somehow I end up with an L and an R that never converge. Can I just say -1? Seems like it. We're getting closer. So for this test case, the best answer is going to be buy here, sell here, buy here, sell here. This one's going to give you a profit of 3. 1 for this, 1 for this. What are we saying our left and right sides are? Our left and right candidates are? Left candidates are 0, 1, 2. So yeah, you 1 profit from here, and then 2 to 6. That means you end here and you have a profit of 2, which would mean you bought here. So yeah, these are the left candidates. I see a problem because 2, 6 should also be a right candidate. No, because its index is the left side. So 1, 5. Wait. Yeah, okay. 1, 5. So 0, 1, 2, 3, 4, 5. So it's saying this gives a profit of 1. This gives a profit of 4. Oh. Yeah. So why didn't I end up matching this with this? Technically I shouldn't need this if, because that's what I should be getting from my binary search. Although there may not be an answer, so maybe I do need the F. Okay, so what am I getting from the binary search? Print binary search found. And then for index, it found right candidate. For 2, it found 1, 5. So the thing is, these are both valid. It's just that I wanted the best one. I wanted the one closest to 2, which would be 4. It gave me the wrong one. So let's look at the binary search. I'm looking for 2. Index is 2. Oh, this is probably because of the because of my -1 here that I am not sure if I actually needed. Thing is, at a certain point, it stops shrinking. Once this is like size 2, so this is not the right way to do this, but if right candidates of R, I'd rather give the right most one, because that's the one with the bigger score. Wait, maybe this binary search is not the right thing to do. Yeah, what I want is the rightmost one in this list. Which is to say the smallest index. I want the smallest index, which gives the right answer, or which is I want the smallest index where start is greater than index. Oh, I'm just the fact that all these lists are in like different orders and I have to keep it all in my head is really messing with me. So right candidates is sorted in increasing order of profit and decreasing order of left index. So I'm trying to find the largest the smallest left index. I want the smallest left index that is greater than start. I want the smallest start that is greater than index. So take the midpoint. If the midpoint's index is less than or equal to index, if R is greater than L, return right candidates of R. Because I want the one farthest to the right. Like, this is a stupid way to do it, but I think this is what I want. It's not. Why aren't you giving me 2, 4? 4 should be the smallest index greater than 2. What do we have at the end here? Print right candidates sliced from L to R. 1.15, so we've already gotten rid of the thing we're looking for. So we must not be doing this properly. If our midpoint is less than or equal to the index, that means our midpoint cannot be the answer, so we can do plus or minus 1 on it. Our solution is on what side of it? So the indexes are in increasing order. No, sorry, the indexes are of right candidates are in decreasing order. The indexes are in decreasing order. The one that I'm considering is less than index. I want a bigger one. The bigger ones are on the left. So I shrink the right side to the middle. If the one I'm considering is greater than index, then the one I'm considering could be the answer. And the other ones that could be the answer and might be even better are, so the midpoint might be the answer. The other ones that might be the answer, the indexes are in decreasing order. So the other ones that might be the answer are on the on the left, but I said left both times. What? Hold on. The midpoint is already a possible candidate. The others that might be even smaller are on the right, actually. So mid should be included, and the others that are even smaller are on the right, which means we want to shrink the left side to include the mid. So this is right, but how am I losing the right answer? Oh, how many more times am I going to have to go through this before I figure out that I just did something backwards? Oh, wait. If I'm slicing L to R, maybe print L and R. L and R. Maybe my slice is just weird. Okay. But yeah, I want the rightmost one. Right? If I have multiple things that might be the answer. No, the thing is, I'm just getting confused. I just haven't shrunk my search space far enough, and I don't, of the things that are left, I don't know which one's the answer. So don't just take the thing that's farthest right. Do if right candidates of R of 1 is greater than index, then you can return that. Otherwise, return the other one. Okay. I think this one will finally work. Knock on wood. N log n. We did it. We finally did it. And I don't know if there's an ON way to do this. I'll be curious to read people's answers. We're in the pack, you know, beat 38%. I have a feeling there's an ON way to do it, but we found this wacky ON log n way, which is pretty cool. All right, how did other people do this? Dynamic programming. Dynamic programming, huh? Dynamic programming. Oh. Oh. So the thing I said way at the beginning of on each day you either do a transaction or you don't. I think that's the way to think about this. And then this is the two dimensions here. Are these like transaction 1, transaction 2? They are doing it linearly. For us, k is 2. Buy 1, buy 2. This isn't dynamic programming anymore. This is more like the thing we were trying to write at the beginning that we decided doesn't work because we might want to go back in time. Yeah, this is literally that idea where you are generating candidates for the buy 1 for the first transaction as you go, and your second transactions are based on your first transaction. And the thing I thought was that you might have to like go back in time and make a different first transaction. Very interesting. I'm trying to see if someone has an explanation for why my back in time thing is not a concern. State machine. It's so interesting that this very first idea, it is just as simple as it looks, it seems. Something I'm not understanding is how are they tracking the buy Oh, because they're just doing they're doing something weird. Instead of doing maxes and mins, they're doing maxes over negative prices. Yeah, it really is as simple as the very first idea that I dismissed. And this seems right to me now. I'm having, like, what was my objection? It was like, you, your solution, your the first transaction in your two transaction thing that you're keeping track of might not be, you might want to go back in time and buy at a different time. I think we managed to get rid of that concern when we were thinking through the matching stuff, when we decided that the buy time always moves forward. That would have let us go all the way back to doing it n instead of n log n. Okay. Well, that's interesting. Next problem. Start the stopwatch. 124, binary tree maximum path sum. Hard. A path in a binary tree is a sequence of nodes where each pair of adjacent nodes in the sequence has an edge connecting them. A node can only appear in the sequence at most once. Note that the path does not need to pass through the root. The path sum of a path is the sum of the node's values in the path. Given the root of a binary tree, return the maximum path sum of any non-empty path. Okay. So I happen to know that in a general graph, finding the longest path is an NP complete problem. So you can't, there's no known way to do better than exponential. They're giving us a tree, so there probably is a way to do better than exponential, because the graph is so much more structured. It's not a binary search tree, right? No. It's a binary tree. So every node has at most 3 connections. That may be important. Let's think about it. So the path with the and there are negatives also. That makes sense. Otherwise, it would be a little easier because you could just go through the longest path. Or not exactly, but whatever. It makes it harder that there's negatives. So this is very interesting. So I'm getting flashbacks to a previous Leetcode problem that was find the largest contiguous subset in a list, where it had this property where you could grab some stuff on the left if it was larger than the amount the negative amount you'd have to pick up by getting over there. So in this case, there's a 9 on the left side of this -10. It's never going to be worth picking up the 9 because you're going to end up with -1 overall, because you can't pick up this 9 without going through this -10. So I wonder if there's some dynamic programming kind of thing where I can say, I will pick up this -10. Like the real value of this -10 is -1. Of this node is -1 because that's the value of it plus the best path that you can grab from it. Let's think of some other structural stuff. So it's a binary tree. I think we can say a binary tree will take... There was only going to be one node where we go down the left and the right path of it. Like, it kind of like our path will be a tree that only has one root. Like in this example, it's like our root is 20 and we take one line down both sides. The reason is you can't, like, how would you end up with two different nodes where we take the left and right side of them? Like, you can't go back to grab the 20 again. It said that. Otherwise you could get infinity. Where does it say that? A node can appear at most once. So you can't go to 7 and then go back to 20. So how else would you end up getting two nodes with both sides? Like, could I get both sides of this and both sides of this? No, because once I go down one path, I can't get back to 20. Because everything has exactly one parent. Like, that's clear to me. I'm not sure that I explained that well, but you're only going to be able to get one node where you pick up its left and its right side. So the answer is basically like, find the node where left plus right is maxed. And then for each node, because every node other than that root node, you're only going to go down one path. That means for each node, its value is whatever is max between left and right. So that would mean plus itself. So I mean, this is 9, this is 15, this is 7, this is 15, this is 15, because you, 15 plus 20. Sorry, I said this is 15. This is 15 plus 20, so this is 35. This one is 25, because it's 35 from the right side versus 9 on the left side, plus itself, which is -10. So that's like the value of each node. And then what you want to do is, for each node, check if it was the root, what would its tree value be? So then you have, I believe, ON for the pre-processing of finding the value of each node, and then pre-processing to find value of each node, and then another ON to consider each node as possible root. Okay, so let's do that. Yeah, this is like a classic dynamic programming thing, it seems like, where I'm just trying to think, how am I going to store the values of the nodes? Maybe I'll just have a dictionary. So values is a dictionary. Oops. We want to iterate over the nodes, so we'll just do a little tree traversal for node. Yeah, so this def traverse node, tree node, or none. Traverse node dot left, traverse node dot right, and deal with node. So node dot value equals, or the values of this node is equal to the max of myself, so node dot val plus whichever is bigger between values of node dot left and values of node dot right. Let's traverse first so that we go from bottom to top, and then we'll deal with our own values after we're done traversing. Traverse. So technically this is you know, the tree traversal makes this use more space than we want, or than O1. So the tree traversal makes us use ON space. I think you could probably redo this in a non-recursive way. I'm not sure, but let's not care about that. Traverse root. Okay, so now we've got all the values. Now we want to try consider each node. So we're going to traverse again. Def traverse to node, tree node, or none. And I forgot here, if node is none, return 0. Okay, so now let's do this again. Traverse to. Node dot left, traverse to node dot right. Here the order doesn't matter, so let's just do a reorder. Here, best equals negative infinity from math import infinity. Best equals max of values. You know what? This one doesn't even need to be a node. We don't even need to do a tree traversal here. We can just do for node in values.keys, which is the same as not saying keys. Best equals node dot val plus values of node dot left plus values of node dot right. The other thing I'm realizing is the only thing you need is the values of the children, which means we can just do it as part of our traversal up there. So instead of generating the values and then doing some other thing, like instead of iterating over it twice, we'll just iterate over it once and return best. Best is max of the current best and this new candidate. Keyer. So there's not supposed to be a keyer because I was traversing in the right order. So how did I end up with a keyer? Oh. Okay, this is kind of weird, but the fake nodes don't just have a value of 0. I'm also forgetting to return. What am I returning here? I don't need to return anything. I'm just traversing, so just return. Yeah, best is defined out here, and I'm doing some shenanigans. I think you have to do non-local best so for it to take the value from outside the scope. There it is. Let's submit it. Wrong answer, 69 in. Output 1, expected 2. Oh, I'm assuming that you have to go all the way down the path. But I guess it's saying you can start in the middle, like you don't have to... You don't have to go all the way down to the leaf. So I actually want to put 0 in here. Like you're allowed to go down the left or the right or nothing. You can just end there. And I should do the same here. Okay. Once I'm considering you as the root, like I think the other way to say that is you can go down neither. How do I say that? It's kind of like I took 2 as my root and I didn't go down either side. So I figured out that that's a value of 2, but I didn't figure out that that's a thing you can do from the path, from the root. So what I want to say is either you're the best of these or you're just node.val. And I think another way to say that is you can always just not take the value of a... No. Yes. I think the values should be capped at 0 because you can always just go, just not even include this in your path. That's such a weird way to say it. I think instead I'm just going to say you either take Yeah, I think that is the right way to say it. So your values are capped at 0. Min of 0 and this stuff. I guess that's not the right way to say it. The thing I just want to say is the root is allowed to not include the left and the right. It's like you can take the left and the right, or you can take only the left, or you can take only the right, or you can take neither of them. This is such a wacky way to say this. Okay, that works, but let's say this in a less crazy way. So what I want to do is just say, take the best between the best and yourself plus your children. And then I just want to say values is allowed to be 0. Like you're allowed to just, the value of the path can just be the path that doesn't include any of the nodes in this path. So that's what I was trying to do by setting the min of values at 0. I'm not sure why that didn't work. The only time I use values here. That's what I'm trying to do with this 0 also. So why can't I just say min of 0 and this? Because what I want to say is max, not min. That was the only problem. Okay, this is a less crazy version. Okay, I'm happy with that. On to the next one. Start the timer. 125, valid palindrome. Easy. A phrase is a palindrome if, after converting all uppercase letters into lowercase letters and removing all non-alphanumeric characters, it reads the same forward and backward. Alphanumeric characters include letters and numbers. Given a string S, return true if it is a palindrome and false otherwise. I mean, in Python you can just do return S dot lower equals S dot lower. That gives the right answer. It does not give the right answer? I mean, maybe this doesn't turn it back into a string. Do I just need to do string of reverse. Oh, removing alphanumeric. Okay. Okay, well, let's not try to cheese it. Let's just do it the way it wants. We can do a two-pointer thing where ij equals 0 and length of s minus 1. And then while j is greater or equal to 0, if s of I is not equal to s of j, return false, and if we get through the whole thing, return true. And then skip non-alphanumeric characters. So let's just say left equals s of I dot lower, right equals s of j dot lower. If left not in A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z, then left, or then I increases. So skip over it. And space, right? Space is included. Space should not be included. Space is not included. If right not in this, then move the right pointer to the left. I can get rid of these continues by just making these LFs. So increment the left one if it doesn't count. Increment the right one if it doesn't count. No, I do need the continues. So if left equals right, then decrement both, or like increment I and decrement j. I think this works. I can tidy it up a little bit. How does that happen? Oh, because you skipped everything. But shouldn't J... Oh, because we only skipped the left side. Okay. And I is less than or equal to whatever that less than. We got pretty far, but what is this edge case? 0 uppercase P. Oh, alphanumeric. 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay. Let's clean this up a little bit. So, one of the things that's bothering me is these continues and this else. Like this can be a little thing there. Okay, so we can just say if it's not equal to right, return false. And then just decrement just in the normal way. I think that's as much golfing as I feel like doing. I'm not going to get it to be much faster than this. Like you could, but it wouldn't algorithmically make it better. It would just be like using regular expressions or other things like this. This is like 26 times slower than it needs to be because I'm iterating over a list of 26, but it's still a constant factor. So I'm not worried about it. All right. That was 125, so that's it for today. Thanks for watching.